Hi, everybody. Very, very exciting section 5.3. It's the fundamental theorem of calculus. The entire semester will culminate in this section. We're going to see the connection between finding the areas of these curved regions and slopes of tangent lines, integrals, and derivatives. Finally, it's a big one. Let's check it out. Okay, we're going to start where we left off last section with the definition of the definite integral. So we introduced this new integral notation. We've got this stretched out sort of line, and it looks real fancy when it's typed. It's a stretched capital S. At the bottom is A, at the top is B, f of x dx. That is telling us to find the definite integral from A to B of f of x dx, and graphically, that is the exact area beneath, or I should say between the function and the x-axis, starting at A, ending at B. How did we learn how to do that? We said, hey, let's apply this limit of the summation. And essentially what that limit of the summation is doing, we're adding, or we're finding the sum of infinitely many, infinitely narrow rectangles. So the stretched S for the sum, what are we summing? Well, we're taking the limit as n approaches infinity for this summation of n terms. We're adding infinitely many terms. And those are the areas of infinitely many little rectangles. Okay, and of course, if they're infinitely many, they're infinitely narrow. But not zero, just infinitely close to it. Okay. So where to go from here? Okay, so we want a much, much faster method to do these definite integrals than the limit of a summation the way we were doing them, just based purely off the definition in 5.2. Okay, well, where do we go? All right, let's check this out. Let's check this out. We're going to introduce a new function. Let's call it capital F of x. Let capital F of x be the area from negative infinity all the way up to x. And what we mean is the area between the function and the x-axis. But we're going to say capital F of x, we start at negative infinity. So think of, for this function here, think of all the infinite area, right, going backwards, whatever that would mean. All of that area up until our x value, whatever we decide that is. Okay, so if we say an x value, that means find all of the infinite area up to that x value. Okay. Well, what would that imply about the area that is graphed here in green, right? We could then rewrite what our definite integral is equal to much, much simpler. We could say the definite integral from a to b f of x dx is equal to capital F of b minus capital F of a. How can we do that? Okay, well, just think about how capital F is defined. It's all of the area, and if you think f of b, all of the infinite area up to b, but then we're going to subtract all of the infinite area up to a. Well, if we subtract those, what's left? Just the area between a and b. We'd be left with exactly what we want. Okay, well, that's nice, I suppose, but what is this capital F of x? So we'll go on to the next slide here and sort of repeat what will be needed just for where this goes. Okay, so we introduced capital F of x right back when we learned about antiderivatives. But we're going to pretend like we don't know that, okay, right? I mean, we got to prove it. That's what we're going to show here. What's up with this capital F of x function? Really, the question that we're getting at is, how is little f of x related to capital F of X, right? In a question, I will know what my function is that I'm trying to find the area under, that I'm trying to find the integral of, little f of X. Is it possible to figure out what capital F of X is based on little f of X? Again, we know that it's going to be to take an antiderivative, but let's see where all that comes from. It is really, okay, this is so exciting. Okay, how is little f of X related to capital F of X? Let's think about it this way. This is like genius right here. Okay, just think about one little small, pretty narrow rectangle. It does have some width to it. Obviously, this rectangle drawn here is not infinitely narrow because we got to be able to visualize it for now. Okay, so I'm going to draw a little rectangle just somewhere in the region between A and B. Okay. And we're going to put the height of that rectangle just for the convenience of the visual here. I'm going to put the height of that rectangle at X on the left side. Okay. We're going to say the width of that rectangle is delta X. Well, that's what we did before when we did Riemann sums. The width of all the rectangles is always delta X. So that would mean this point here on the right side is X plus delta X. And then I'll know where that next location is if the width is delta X. Right? And we notice, if we draw the height there, right, if the rectangle finds its height on the left side, then there's that little bit of a gap right at the top, just the way that this function happens to curve. Okay. With all that in mind, you see the question there below. What's the area of that green rectangle? You say, oh, well, area base times height, or height times base, whatever you want to do. The height of that rectangle is f of X, the function value there, multiplied by its width, f of X times delta X. Okay, sounds good. Is there a way that we could also represent the area of that rectangle, but in terms of capital F of X? I mean, that would be really nice. So it turns out we can, but it won't be equal to what we just have written there. Let me show you. The area of that rectangle, f of X delta X, will be approximated by, check this out, capital F of X plus delta X minus capital F of X. What's up with that? Okay, so capital F X plus delta X, remember what capital F is, all the area up to X. So this is all the infinite area up to that second line there on the right side. Then we're going to subtract all of the area up to the line at X on the left. Well, what would remain is the area between them. But notice capital F does get the area exactly the way that we've defined it. So these are approximately equal because the left side here is just that green rectangle, where the right side also includes that little bit of a gap. So they're not exactly equal, but they're pretty close. There's just that little gap at the top difference. Okay, well, hey, you know what? This is a start. We don't have any quality. We don't know exactly how they're related, but we're getting there. Let's keep going. What can we do from here? All right, this is amazing. We're going to divide by delta X. No problem. Delta X is we're thinking of it as a finite value here. So we'll just divide that over. I mean, we can do that. Okay. And then this part. If we wanted to get an equal sign, if we wanted to get an equals here, what would have to happen? That little bit of a gap needs to disappear, right, for them to be equal. Well, with our idea of limits, we can do that. What would happen if we shrank this rectangle down? So think of taking the right side and pulling it towards the left side. That would make that gap smaller and smaller and smaller, right? Here's what we're going to do. We're going to take the limit as delta x approaches 0. So we're going to say the width of this rectangle approaches 0. It gets infinitely narrow now, finally. What would that mean about the little gap at the top? It would mean that little gap gets infinitely smaller. It will shrink down to nothing. So we can say now, by taking the limit as x approaches 0, now we have equality. F of x is equal to the limit as delta x approaches 0 for capital F of x plus delta x minus f of capital F of x, all divided by delta x. Okay, let's pause right here. Just make sure everything so far has sunk in. What do we see there on the right side? This should look very familiar. It turns out this is the derivative of capital F of x. How? What? Remember the definition of the derivative. We're using delta x here. When we used this before, we used h, but I mean, it's representing a variable, wouldn't matter what we call it, delta x versus h. The limit as h approaches 0, right? Capital F x plus h, all divided by it. That's the definition of the derivative. This right here on the right side is capital F prime of x. So how is little f of x related to big F of x? It's big F of x is the antiderivative. If we were to take the derivative of big F, we would get the little f. Oh my goodness, that's amazing. Okay, without further ado, here it is, the fundamental theorem of calculus. Okay, notice it's the fundamental theorem of calculus part 2. We'll also talk about part 1. I do them in the reverse order of the textbook. I feel it's more dramatic that way. It's more exciting. And I also find it just makes more sense when you learn it to do it in this order. Okay, so anyway, what you're about to see is the fundamental theorem of calculus part 2, as far as our textbook goes. If little f of x is continuous on AB, then the definite integral from a to b of f of x dx is equal to capital F of b minus capital F of a. You're like, okay, great. So if I'm told little f of x, then I can get the big F and I can plug these numbers in, where capital F of x is an antiderivative of little f of x. Yes, we did it. All right, some examples I think is a good idea here. We're going to evaluate the definite integral for both of these. We're going to see just exactly how the fundamental theorem of calculus and this new formula here with the capital F, we're going to see how what that actually looks like in a problem. The idea is, again, it makes our work way simpler than doing the limit of that summation. All right. Example, evaluate the definite integral. Part A, integral from -1 to 3, 2x minus 4 dx. Okay, so here's what we're gonna do. We're going to begin by finding the antiderivative of the function that we see here. All right, so we look at that and we think, all right, well, 2x antiderivative is x squared minus 4 antiderivative is 4x. All right. Now you might think, well, an antiderivative, we should put on plus c. Turns out we don't need the plus c when we do the fundamental theorem of calculus. I will explain that once we're done with this example, and we'll kind of be able to look back and say, oh yeah, okay, I see why we don't need the plus c. So we're just going to get this part. Then check us out. We're going to end up plugging these numbers in. So I'm going to draw a long vertical line, and I'm going to repeat those numbers, 3 on the top, -1 on the bottom. When you see a vertical line like that, that will occur occasionally in math. You can read that as evaluated from. So you would speak this as x squared minus 4x evaluated from -1 to 3. Again, speak it from the bottom to the top, from -1 to 3, just like this is the definite integral from -1 to 3. Okay, what does that mean? It means we're going to plug these numbers in. But when you plug them in, right, always plug in the number on top first, right? It said capital F of B minus capital F of A. Number on top goes in first. And I'm going to put just like some parentheses on it. So 3 squared minus 4 times 3, plugging in that top number. Subtract, and then -1 squared minus 4 times -1. Plug in the lower number. And this is it. We just gotta crunch these numbers and we got our answer. All right, let's see here. This is 9 minus 12. That's -3 minus, what is this? 1 plus 4 is 5. -3 minus 5. Our answer is -8. And we did it. We found it. Okay, so it turns out, I don't know if you recognize it or not, we did this very definite integral as one of the long examples for the limit of the summation back in 5.2. And it took quite a bit of work, but we got that same answer, -8. Here we go. I mean, antiderivative, plug those in, boom, done. That is so amazing. Okay, now let's answer the question, why don't we need the plus C when we find the antiderivative? Let me put that over here. So, you know, it wouldn't be wrong if you did put the plus C there. But nobody does it for a good reason. If you put the plus C there, look at what would happen next. When you plug the numbers in, right, 3 squared minus 4 times 3 plus C minus -1 squared minus 4 times -1 plus C. What would happen when you subtract? The C's would cancel each other out. So for that reason, I mean, that would happen every time. So for that reason, don't put the plus C because we're just going to plug these numbers in and subtract anyway. Don't need it. We don't need it. Okay, we got our answer. Let's check out part B. This is a new one. The definite integral from 0 to 1, t to the third minus 9t. Okay. All right. Interesting. So antiderivatives, that's 1/4 t to the fourth minus 9 over 2t squared. Draw that long vertical line and then 0 to 1. What we're going to do is plug in 1. Plug in the number on top first, subtract, plug in the number on bottom. 0 here is kind of nice. That all goes to 0. So what is this? Let's see, 1/4 minus 9 over 2. Going to grab my calculator for that. That's -17/4 minus 0. Another negative answer. Wow, we got a lot of area negative, right? Means the area is actually below the x-axis. I kind of want to take a look at the graph here. T cubed minus 9t. Let's do that super quick. Y equals. There we go. Y equals, let's see if it'll work with t. I bet it will. Yeah, 9t squared. Oh, it's just 9t. Never mind. There we go. A kind of cubic, okay. And we were going from t equals, oh, they don't like that. We were going from, we'll call it x equals 0 to x equals 1. We were just getting that little bit, but right, it's the area between our red graph and the x-axis. So it's this kind of shape right in there. And yep, that's all negative area. It was negative 17 over 4. Can you believe that? We can get that area exactly. Negative 17 over 4. Wow. Okay. Go back to the lecture. One more example I want to look at before we talk about the fundamental theorem part 1. Let's take a look at this. Evaluate the definite integral for this piecewise function. We're going to look at the definite integral from -3 to 3 f of x dx, where f of x is piecewise. It's negative 4x plus 1 between -3 and 0, and it's x cubed from 0 to 3. Interesting. Okay. Again, evaluating the definite integral, -3 to 3 f of x dx, where f of x is equal to negative 4x plus 1, and then x cubed, 0 less than x less than or equal to 3. Okay. Thinking like, wow, what are we going to do? I mean, a piecewise, if we're going to use the fundamental theorem, like we would need to find antiderivatives, but there's 2 different pieces. So how is this going to work? So it turns out we're going to do each piece separately. We're going to look at negative 4x plus 1, that piece alone, right? If you look back closely at the fundamental theorem, it says that the function has to be continuous. So we'll take this piece just from -3 to 0, and then we'll take this piece just from 0 to 3. So we're going to do it like this. -3 to 3 f of x dx. We're going to say, you know what? Let's think of this as the integral from -3 to 0 f of x dx plus the integral from 0 to 3 f of x dx. And you might remember this property, right? If we're going from A to C, we can go A to B and then B to C, and that will all be fine. So if we look from -3 to 0, right, we're taking our first piece. And then from 0 to 3, we're taking our other piece, like so. Okay, I'm going to do these separately. Let's kind of think like, okay, like what is this part? Negative 4x plus 1, that would be negative 2x squared plus x from -3 to 0. Okay, plug in the 0 first. Sounds good. Then plug in the -3. Okay, so this is 0 minus, what do we have here? 9 times -2, -18, minus 3 is -21, but that's being subtracted. So that's 21. Positive area, all right. And let's do this other piece here. That's 1/4 x to the 4th from 0 to 3. Plugging in the 3. Don't really need these big parentheses. There's only the one term. That'll work right there. Subtract, plug in the 0. Well, let's see. 3 to the 4th. That's 3, 9, 27, 81 over 4 minus 0. 81 over 4. Okay, and then we're going to add those two. So the whole thing together, 21 plus 81 over 4, 165 over 4. We got it. If you wanted to investigate a little bit further, you could look at the graph of our function here. I'll go back over to Desmos. Always enjoy graphing a piecewise. So it was negative 4x plus 1. And if you put in some square brackets, negative 3 to 0, maybe it wasn't square brackets, maybe it was, 3 to 0. What is the problem? Y equals x cubed. Oh man, looks like I forgot how to do this. Oh, let's look it up. Desmos, how to graph piecewise. Oh, okay, gotcha. It is the curlies, but you got to use the less thans. Aha, negative 3. Here we go. Less than x, less than 0, like that. There we go. 0, less than or equal to x, less than or equal to 3. That's it. Okay, we got it. And we went from x equals negative 3 to x equals positive 3. Yeah, oh, we only graphed it to 3, so that's where it stops. Okay, so we got this kind of little chunk. It's actually a trapezoid right there. We found that area to be 21. We found this curved area on the other side to be 81 over 4. So put the two together, 165 over 4. Very nice. Okay, let's stop this video here for sure. Be back with the next one.